All right, so welcome everyone to the 2025-2026 edition of the Schubert Seminar. We're very happy to start a new sequence of seminars. I think we are in the fourth year now of the seminar, and our first speaker today is Irreducible, is Bill Graham from University of Georgia, telling us about irreducible characteristic cycles for orbit closures of a symmetric subgroup. So please take it away, Bill.
Okay, thank you. And thanks to the organizers for inviting me. So I'm going to talk on some joint work with Minyoung, Jeon, and Scott Larson. And, I think to be fair about it, I'm going to be talking about a lot of things at various points, which I don't claim to be expert about, but there are people in the audience who are more expert on various things than me. So maybe they will fill in certain aspects of it. But anyway, let me just get started. And I thought what I would start off by doing is just saying what the main result is in a sort of approximate way, and then maybe go back and try and motivate it. Okay, so oops, let's try and be neat here. So I'm working in the setting where G is the general linear group GLN, and it's going to be containing this subgroup K, which is GLP cross GLQ, where P plus Q is equal to N. I'm going to let X be equal to G mod B, the flag variety. And I'm going to let V be the set of K orbits. Now, what I mean by this is that K orbits on G mod B on X. And so what I mean by this is that this set of K orbits is finite. And so V is just, it's just the enumeration, if you like, of the set of K orbits. So this finite set. And so the notation I'll use is that if given V and V, the orbit will be denoted by X sub V, which is K V dot B mod B. I want this to be the closure of the corresponding orbit. Okay, and V dot is just a representative of the orbit. And so the main theorem is that for certain orbit closures, there is a small resolution I'll call it mu from ZV to XV with smooth and strongly reduced fibers. And strongly reduced is just a condition on the derivative of the map. And I'll say what that is a little later, but as a consequence, the characteristic cycle of the IC sheaf is irreducible. And so I'll talk more about all this stuff in a little later, but the corollary is that, follows from a result of Jones, is that the Chern-Mather class is given by, if I can push forward via this map mu, the Chern class of the tangent bundle of the resolution ZV, I cap it with the fundamental class of ZV. Oops. And this is equal to Cm of X B. And so then what this means is, in fact, is that you can compute in examples for these things, the Chern-Mather classes. And so we conjecture is that, I'll try and write this neatly, is that when expressed in a Schubert basis, Cm of xv is positive or has non-negative coefficients. And similar, and this also works equivariantly. This also for the equivariant Chern-Mather class. Okay, so that's that conjecture is supported by a somewhat admittedly limited amount of computation, but it's still somewhat convincing. So, okay, so that's sort of the main result. And I thought maybe I should ask if there are any questions. I thought what I would do is then briefly sort of try and explain some of the motivation for this and some of the terms involved. I think the invitation suggested that part of the talk should be accessible to non-experts, and that includes the speaker. So I thought I would just go give a little bit of background and motivation if there aren't any questions at this point.
Well, I was going to ask how it relates to statements about B orbits on a Grassmannian.
Well, I mean, the K orbits are different than B orbits. So, I mean, one could say something maybe about K orbit closures in a Grassmannian, but this particular statement has to do with K orbit closures, not B orbits.
Yeah, but undivide by um, instead of taking G and thinking about K acting on there, I was going to take sorry, instead of taking G mod B with K acting on it, I was going to take G mod K with B acting on it.
Yeah, well, I mean, I think it probably implies that if you think of G mod K with
So G mod K is almost a Grassmannian here.
yeah, I guess, but not quite. It's like a fiber bundle over a Grassmannian, I guess. But I think it would imply that those orbits are also have irreducible characteristic cycles because it's sort of a topological kind of thing in the, these things all kind of are fiber bundles over each other with smooth fibers. So I think that would probably work for these kinds of orbit closures. I guess taking the closure, I'd want to think about it a little bit, I guess.
Because, I mean, in that case, we have Zelevinsky giving these small resolutions. So I think that there we know it for all the B orbits on the Grassmannian, not just for
Right.
some of the certain ones.
Right. No, that's right. Well, I mean, presumably in the case of Grassmannians, this result might be, weaker than Zelevinsky's, or maybe one could even prove a stronger result for Grassmannians. In any event, let me just talk a little bit inside this part.
So I had a question also.
Yes.
Probably very simple. So the finitely many orbits, I just can't wrap my head around. There must be a really simple reason for that. I just can't see it.
That I actually have to say I don't know the proof of that off the top of my head, but the example to keep in mind, I think that's sort of persuasive, is if you take GL, well, in general, if you have the fixed point set of a fixed point group of an involution that acts with finitely many orbits, I think if you take GL1 cross GL1 acting on the flag variety of GL2, you see there are 3 orbits, in fact. And that's sort of, there's the 2 T fixed points, because that you just have the torus, and then there's the open orbit there. And in general, I don't think I could provide the proof of that off of the top of my head, but one can describe them combinatorially in a way that's very similar to the Weil group.
Okay, I won't feel so silly. I can't see the reason
Well,
immediately.
I can't.
Thanks.
Yeah, I'm not prepared to tell you the reason for that right now. So,
Let me at least hint to Anders how to index those orbits by something finite, which is so the GLP cross GLQ is the fixed points for conjugating by a matrix with p1s and q minus ones down the diagonal, right? So call that matrix theta, and then given a flag, you can compare the flag to theta times that flag, and they will be in some Schubert position, and that tells you the orbits.
Uh-huh. Okay, thanks. I'll think about that.
okay. Well, thank you for that explanation. Okay, so anyway, let me just say a little bit about this motivation behind this. And so in this part here, I'm really just gonna. I cited this result of Jones above, and so this is really sort of just following some exposition in Jones's paper. But in general, maybe I just should say what the characteristic cycles are. What is a characteristic cycle? Maybe not everybody knows about that. And it's just suppose that X is contained in M, which is smooth, and say M is stratified. And say X is the closure of a stratum. So then there's a constructible sheaf, which is really a complex of sheaves. ICX on M. So it's a complex. Now associated to any complex of sheaves which is constructible with respect to that stratification, there is the characteristic cycle, which is just, it's a formal linear combination of certain conormal bundles of strata, of closures of conormal bundles of strata. So this is a Lagrangian subvariety. And so this is like a Lagrangian cycle. It has dimension equal to the dimension of M. Every component has. And this CIF has a fancy name. It's called the microlocal multiplicity. So the way I would just think about this is the characteristic cycles these are important and somewhat mysterious invariants of singular algebraic varieties. So these are important for this, and the characteristic cycles of k-orbit closures they're related to representations of real Lie groups. So they play a role in the infinite dimensional representations. But for the moment, they're just in this somewhat mysterious invariants of algebraic varieties. Now, other kinds of invariants of singular varieties are Chern classes or variations of these. And let me mention, and I want to think of these as living in homology. So if X is smooth, we have the Chern, the the total Chern class in its homology version sitting inside the Chow groups of X. But then let me mention there's a couple of generalizations to singular X. So the first one is this CSM class, which comes from, there's a unique map. So McPherson proved that there's a map C star from constructible functions to the Chow groups of X, such that C star of 1 of X equals C of Tx cap X if X is smooth, and C star commutes with proper push forward. And so so this is McPherson. And then CSM of X is C star of the constant function on X. The other thing is the Chern-Mather class. So there's something called the Nash blowup. X tilde may not be smooth, but it has a bundle call it S, which is a kind of a replacement for the tangent bundle. And the Chern-Mather class of X is equal to the push forward of the total Chern class of this bundle capped with X tilde. And again, the point of this is just that these invariants are kind of all related to each other. So for example, CSM of X can be expressed in terms of the Chern-Mather classes of the closures of stratum, where this Fij is related to these sort of some local Euler it's like an inverse matrix to local Euler instructions. So I mean, this is not really important, but it's just the point is just to try and say that there's this landscape of invariants. And my understanding of the general landscape is also that CSM of X is generally easier than the Chern-Mather class of X because of this functorial property. But Jones proved if X contained in M is as above, and X admits a small resolution, and the characteristic cycle is irreducible, which means is just this, there's just one term in this, which is the stratum corresponding to X itself. Then the Chern-Mather class of X is just the push forward of the total, where mu is this resolution.
So A doesn't imply B?
I don't think A implies B in general. At least he certainly, I mean, I don't know too many concrete examples, but he certainly states these as separate assumptions.
Yes, small resolution just says that you push forward, you get the class of the IC sheaf. And then there's still a question whether the IC sheaf is equal to the Mather class. And that you need irreducibility for that, I think.
Okay, so in any event, the point is that, so what Jones actually says in his paper is that Schubert varieties, this is, I guess, sort of related to what Alan was remarking on earlier, is that Schubert varieties in Grassmannians and some other examples in classical types satisfy A and B, but he's not aware of any other examples. So maybe there are other examples known now, I don't know, but the point is, it seems interesting to therefore to look for varieties where this might these hypotheses might hold. And so one of the things we prove is that, in fact, that in general, if, given a small resolution, I mean, so this is maybe in relation to Alan's question, if you put another hypothesis on the small resolution, then you can get the irreducibility of the characteristic cycle. But whether you can get away from this, I don't have a concrete example. But given from Z to X small resolution, such that the fibers are smooth and strongly reduced, the characteristic cycle of IC of X is irreducible. And strongly reduced means this means that if you have a fiber which is the inverse image of some X, then what you want is that, and so you can think of this as, if you like, you can think of this as a map going to M. So your target, if you want it, is the smooth variety. Then what you want is that if you look at the kernel of the derivative of mu at any point Z for Z in the fiber, this has to equal the tangent space of the fiber. So there's the inclusion that the tangent space of this inclusion is clear, and then you need something to prove in the other direction. So under this condition, the characteristic cycle is irreducible. Okay, so maybe I'll pause there and ask if there are any questions.
I'll have a quick question. So in your situation where you have this compact group acting.
No, K is not compact.
I'm sorry, where do you have the K acting? So the product of the GLs.
Yes.
Is it easy to calculate the IC sheaf? Like the class of the IC sheaf? Every time when you have a characteristic cycle, there is also a characteristic class associated to it.
Well, I think I think in this case, this is a small resolution. I think one could probably calculate things for this when you have a small resolution. In general, I don't know how you would calculate the IC sheaf otherwise.
So the Kazan-Lustig polynomials, right? You have a
Yeah.
simplification.
There's these Kazan-Lustig Vogel polynomials, which I guess calculate these IC sheaves. So there's some kinds of Kazan-Lustig polynomials in this setting. I have not ever tried to calculate them.
Okay. Thank you.
Okay. So let me move on to just a couple of things about these K orbits. And their closures. So in general, I mean, let's just, in the interest of time, I mean, a lot of this stuff can be phrased in the setting of, you have in general, you have an involution of G, and K is either G theta or close to it. In other words, it's between the G theta and the identity component of G theta. Much of this stuff, or certain things, work in this general setting, but I'll just, much of this. So there's very many generalities, but we'll focus on this because, the main results we have use some combinatorics that are special to this setting. So I'm just going to focus on this setting for us. G is GLN, and this is contained in K, which is GL P cross GLQ. Now, before telling you what the parameter set for the set of orbits is, I'll just say this is going to be the set of orbits. And it has a kind of Bruja order. These are K orbits, as I said before, on G mod B. This has a kind of Bruja order, which is just the closure ordering. And then there's what's, S, I'm going to take W as usual to be the Weil group. S is going to be just the SI, the simple reflections, not to be confused with strata. And so then given V in V and S in S, I can define V star of S to be equal to the unique open K orbit in K V naught dot PS mod B. And so then this is called the monoid action. This is all due to Richardson and Springer, by the way. And, then of course, either V star S, it's possible for that to equal V, or V star S, it's one dimension bigger than V, and it contains V in its closure, that orbit. And the braid relations are satisfied. And, V star S is just the same as V star S. So one little bit of combinatorial thing that's useful to keep handy is tau of V is you want to look at the simple reflections such that V star S is equal to V. That's somehow called the tau invariant, and it's useful for various things later. So in our case, the V has a concrete description. I'm not really sure who this is due to, but I've seen references to Yamamoto. V corresponds to these things which are called clans. And we could say this is VPQ if we need to specify. And so a clan, it's a sequence of symbols A1 up to AN, where AI is it's either a plus sign, a minus sign, or an integer, subject to the number of plus signs plus the number of pairs equals P, the number of minus signs plus the number of pairs equals Q. And clans are, so for example, we could have 1 plus, and every natural number occurs twice. So for example, we could consider 1 plus 2, 1, 2, and this would be in V3, 2. And there's one convention, which is that we only really are concerned with the positions where the natural numbers occur. So 2 clans are considered the same if they only by the values in the matching positions. So what I mean is by this is that this is equal to 2 plus 1, 2, 1. Like, I don't care whether there's 1s and 2s there. I'm really just keeping track. The numbers are just to keep track of which entries are paired with each other. Okay, so in this setup, everything can be described very concretely. And so let me take a minute or two to do this, and then maybe we'll take a break in a second. But I don't know whether it's a good idea to start this talk this semester with a very concrete talk or a very abstract talk, but I'm just going to we'll start at a very concrete level. So in this setup, everything is very, well known, I would say. So the closed orbits, these correspond to V consists only of signs. There's one open orbit. And so what it is, it's going to look either like 1, 2 up to P minus P 2, 1, or it's going to look 1, 2 up to Q plus Q 2, 1. So it's something which has all numbers at the ends in sort of increasing order at the left and decreasing order at the right. It's got as many numbers as possible, and it's got, because you can't have, if P is bigger than Q, you can't have more than Q, pairs. And then the number of signs in the middle is to make the condition that these numbers work out right. So you're basically putting as many numbers as you can on the opposite ends in increasing order on the left and decreasing order on the right. So that's the open orbit. This is if Q is less than or equal to P, and if P is less than or equal to Q, I guess. And then now one thing that's interesting is that I want to tell you what some of the orbit closures are actually smooth. And it's known, even if the orbit is not closed, it may be smooth. And let me tell you what the smooth orbit closures are, because that will be useful to us. So the smooth orbit closure is something. It's something that has a block. V naught is smooth. Is of the form. So let's just call this element VPQ max, because it's the largest element in the Bruhat order that's a clan of type PQ. So V naught is going to be something that's obtained by concatenating clans, so each VI is it's the maximal element in a PI QI clan. So for example, if I had something like 1 plus 1, 2, 2. That clan, this is like V1, and this is V2. And this is the clan, this clan V0 is, I could write as V1, V2. So it has a kind of a block decomposition like this. This is the maximal element. The 1 plus 1 is the maximal element is V max 2, 1, and this is V max 1, comma 1. So to have a block decomposition like this just means that in each block, in general, you can write V as V1 up to VR as a block decomposition. Just means that all the mates occur within blocks. So if a number occurs in a block, its mate has to occur within the same block. And that's the definition of a clan. Is that the clan has to occur, the clan has to, the number, each number has to have a mate. Okay. So maybe I'll stop and take a break since I'm sort of moving along. Time seems to be slipping faster now, going by faster now than anticipated. Maybe I'll take a brief break and continue in a few minutes.
Yeah, sounds great. Thank you very much. Let's take a break, 3 minutes until 5:10.